Thank you. Thank you very much for the invitation to speak here. I'm sorry I couldn't have been there in person. Right, so this is going to be a discussion of some joint work that was done with multiple collaborators. So Peter Constantine, Dan Ginsberg, Michela Dolce, and Tarek El-Gindi. So I'll just start with the very basics, remind everybody what the equations are. So we're considering perfect fluid, so inviscid and incompressible in a two-dimensional bounded domain. Say it's something like a disk. The Euler equation for the momentum of the fluid is this usual one. The volume preservation is encoded by the velocity being divergence-free, and the non-penetration condition means that the velocity is tangent to the boundary. Okay. We're going to be working in two dimensions throughout this talk, so there's a couple of simplifications that you can identify there. First, since the velocity field is divergence-free, there's a Hamiltonian function, psi, stream function, for which the velocity can be written as the Stoke gradient of the stream, so rotated gradient. And this is called the stream function simply because if you look at levels of psi, those curves are integral curves of u. So u is just tangent to level curves of psi. Those are streamlines. The fact that u is tangent to the boundary just means that psi, the stream function, should be constant there. Namely, the boundary should be a streamline. Now, another simplification, so that one was sort of kinematic, just the structure of the velocity. This one is dynamic. So in 2D, if you regard it as a 3D flow with vertical symmetry, then the vorticity field is just pointing in the up direction and has a scalar prefactor that depends on the coordinates in the plane. So that scalar prefactor, in fact, is the two-dimensional curl of the velocity u. So it's this particular combination of derivatives. And in terms of the stream function, it's just the Laplacian of it. And the Euler equations actually tell you that this vorticity scalar is transported. So it's just moved by the Lagrangian flow of u. And of course, this can be closed as a non-local equation for the scalar field by means of the BS of R law. So you can recover u from omega by some integral operator. And these equations are equivalent in the Lagrangian formulation to just saying that your vorticity field is some area preserving rearrangement of the initial data, where the thing you rearrange by is constructed from the velocity u. Okay, so the first question you ask when you have such an equation are, what are the first integrals? So what are its conservation laws? And in general, there's sort of two robust classes of these. One is the kinetic energy of the fluid, so just the L2 norm of the velocity field that's preserved, and that just uses tangential boundary conditions and incompressibility. And the second, using the same, are the Casimir. So any continuous function of the vorticity is an integral of motion. And that's simply because the vorticity is area preserving rearrangement, so you can change variables and you keep the same behavior. So LP norms is just one example. There are sometimes additional invariants. So if your domain has symmetry, like Euclidean symmetry on the torus or the channel or the disk, then you have some momenta. So either linear momentum or angular momentum. But these type of integrals are not robust under perturbation of the domain. Okay, so the first point is that the fact that you have these conservation laws allow you to prove global well-posedness of the 2D Euler system. So this is a very classical result, that if you take a velocity field, which is, say, C1 alpha, so one derivative is Hölder continuous with exponent alpha, which just means, in this case, the vorticity is Hölder with exponent alpha, then there's a solution in that class for all time. But the solution can sort of grow there. So the best bound you can get from general proofs is that the size of the solution in that space can be double exponentially big in time. And in fact, this is known to be sharp now. So there's a construction by Kiselev and Sherek that realizes this on the domain of a disk. Now, we're going to come to this point a bit later, but it matters a lot what topology you're talking about the solution in if you're interested in the behavior at long time. This C1 alpha phase space is not compact for the solution because it can leave it at infinite time. But a very important space for which the dynamics are compact is this Udovich space. If you just take vorticity and L infinity, then the fact that you have these Casimirs means that you're always bounded by your initial data in that space. So you never leave, you never get far. And so we'll come back to this point, but this Udovich space, just bounded vorticity, is crucially important to understand the picture of the fluid at long time. Okay. So since we're interested in these persistent behaviors, a natural place to start is just to understand steady states. And this is already an extremely rich area, which is far from being well understood. The first point is that a steady vorticity distribution just satisfies this equation. So transported, transport by U does not rearrange the profile. And if you write U in terms of the stream, it's just saying that the gradients of vorticity and the gradients of the stream are parallel. Okay, and so there are some very well-known examples of this situation. Shear flows, where the velocity is just down the channel and it can change in intensity as you go across, or circular flows, which are a natural analog of that structure on a disk or an annulus. And these structurally satisfy this property, so any such is a steady state. Another big class, which is easy to generalize to different domains. See, these ones required the symmetry of the boundary, Euclidean symmetry, to just write down. But if you don't have that type of symmetry, there's still a very large class of steady states you can study. Those come from declaring a functional relationship between the vorticity and the stream function, so that this condition of collinearity of the gradients is just automatically satisfied if you can identify. And what this boils down to, since vorticity is Laplacian of the stream by definition, this boils down to just trying to solve this elliptic problem, semi-linear elliptic problem for a stream function C, given boundary conditions that ensure the velocity is tangent. And this equation in general is not a good one in the sense that it can have no solutions, it can have many solutions, and it can have unique solutions. So it depends on the character of F. A good example of that is just the eigenfunction equation if F is linear. But there are some cases where it really is solvable, and those cases also correspond to physically relevant ones because those are stable. I mean, so general solvable ones. So these are called Arnold stable states, and they come from declaring this F has one of two properties, either that F's derivative is negative, but bigger than the minus first eigenvalue of Laplacian on the domain, or F's derivative is positive. These correspond to maximizers and minimizers of the kinetic energy on the sort of sheet of rearrangements of the initial vorticity function. So there's some geometric picture to what these two conditions mean that was elucidated by Arnold. And the dynamical point about these is that if you can, I mean, any such is actually orbitally stable in L2 of vorticity. So if you desire to stay in some given L2 neighborhood of the initial point, you can always find a ball for which any perturbation meets that desire. And so they are certainly relevant to the long time behavior. One interesting point about them is that they always inherit the symmetries of the background domains. So on the disk, these are all circular flows, and on the channel, they're all shears. Yeah. Okay, so the difficulty in understanding behavior nearby steady states for Euler is that they come in infinite dimensional families. So there's really very many of them, and you don't know sort of which one you're going to look like, or if you look like one at long time. And there's a couple of results that kind of quantify this. One of them is by Chauffroux and Schwerak in 2010, that say, given a certain Arnold stable state on an annular domain, there's this very interesting property that if you perturb its vorticity, so you look in a neighborhood of the vorticity, each distribution function corresponds to having a unique stationary state on its coadjoint orbit. Now, the coadjoint orbit is just the collection of vorticity fields which can be rearranged by a volume-preserving transformation of the given one that you have. So it's saying for each initial vorticity profile nearby a steady state, you can find a unique steady state on this set. So it's really characterizing completely in a neighborhood of that one, the structure of the steady states. And it's an infinite dimensional family in one-to-one correspondence with the distribution function. Another result in this direction that I'm not going to dwell on is studying a similar issue, but not for a coadjoint orbit of the vorticity, but rather the orbit of a stream function. And in this theorem, you can also say that if you deform the domain, there are nearby steady states that assume the deformed structure. So, okay, I won't dwell on it, but the main point here is that there are many steady states. There's another issue for understanding long-time behavior, which is that being an infinite dimensional system, many of the lessons learned in finite dimensions don't directly apply. So there was this example that Nadarashvili gave in the 90s for wandering domains. What it means is that he identifies a point in the phase space Xi with the property that if you start sufficiently close to Xi in a topology, so it's actually L infinity vorticity, but let's just say in a topology where the Euler equation makes sense and it's a dynamical system, you start close and you just forever leave. So you never recur to this neighborhood. And so it's like a counterexample to Poincare recurrence, naively interpreted in infinite dimensions. And his point C is easy to explain. So you just take a periodic channel and you look at a stable shear profile, say Couette flow, and C is obtained by adding to Couette flow a little vorticity perturbation that connects the top and bottom boundaries. Assume some value on the line connecting it, but a small perturbation. And now the point is that if you start with this one, or if you start with anything close to this one, what happens because of stability of the background shear is that this point moves much faster than this point. And so it wraps around the channel many, many times. But that means that after some fixed time, there's always some yellow on this side of the torus, of the channel, whereas for the initial point, there's no. And that's actually directly saying you leave an L infinity neighborhood of your initial point. And that's true for an open set in L infinity around this point. So it looks kind of simple. It is simple. But conceptually, it's important because what it means is that in this topology, L infinity, and on the natural phase space for Euler, which is actually the restriction of L infinity in the sense that you really can only move on volume-preserving rearrangements of your data with the same energy. That's what you know from the conservation laws. That's potentially a much smaller set. And what it's saying is that in this phase space, you cannot be ergodic. There are regions that you go through and then you just never come back. And so it's a conceptually important result. You can sort of enhance this result a little bit by just noting that the length of this line is forced to grow at least linearly in time. And that actually tells you that the C1 alpha norms have to diverge at least like T to the alpha. So not only does this give a wandering result, but it also gives an infinite time blow up result for Euler in C1 alpha spaces. So you really leave the phase space at infinite time. Of course, you don't leave L infinity, but you leave C1 alpha. And there's been a lot of work on a similar type of results. I just list the names, but I don't have time to mention it. Let me just say that this leaving C1 alpha is a very natural thing, because it means that there's some vortex filamentation going on. You take a small tube of vorticity, it gets mixed around, and it has to get very thin, so the gradients have to get very big. So it's a very natural thing. And you would expect that it holds sort of generically, and in particular, it should hold near all steady states. And so a result in this direction was provided by Koch in 2002, and subsequently Margulis, Schnirelman, and Udovich, which basically says that there's a finite time result that ensures that what I just said is really true. It says that for any stationary solution of Euler, with a certain property that we're going to talk about at some length, that the Lagrangian flow map is not time periodic, which I'll just call isochronal. I'll explain it in a second. Then it's non-linearly unstable in C1 alpha, which just means that you can start close. You can find examples which start close in C1 alpha, as close as you like, and get as far as you like in C1 alpha. So you get really big at some time. It doesn't ensure that you can't potentially come back, but that's extremely unlikely, but it's not proved by this theorem. I won't really talk about the proof of this, but let me just say which flows are excluded. So the flows that are excluded are these periodic flow map ones, isochronal. What it means is that if here's a domain and there's some fluid inside and it's moving things around, let's just make these arrows out of passive tracer, then those will just go around this domain. And isochronal ones have the property that at some later time, they come back exactly to their original configuration. So the flow map is a time periodic function. It's sort of like a fluid clock. And the reason why the proof doesn't work for this is that the proof relies on some sustained filamentation by the background flow. And the point is, while these things might get sort of stretched and folded here, they eventually come back to their original configuration, so it's all undone. Okay. Nevertheless, you would expect that these things also have the instability property, because there should be close by things that do shear. And so let me give you some evidence to that. So first, they're kind of interesting objects by themselves. And Udovich conjectured that among constant vorticity ones, so one example, by the way, is just solid body rotation, like a record player. That's a stationary Euler solution with constant vorticity. And you can generalize that to be on ellipses instead of a disk. And Udovich conjectured that the only constant vorticity ones are those elliptical sort of record players. This is still open. However, with Tarek, we were thinking about more generally the structure of the set of isochronal things. And we believe that for any simply connected domain, there's at least one of them. Without dealing with what the vorticity profile is, there's at least one. So they're not so special, but maybe they're unique in some sense, given a domain. And so here's a result for that direction. Suppose you take a slight deformation of a disk domain, then there's a unique isochronal flow on that new domain. And the proof of that is just the observation that if you have an isochronal flow and it has a certain stream function psi, if you rearrange that stream function by an area preserving transformation, the result will always be isochronal. And that's simply because isochronality means that the travel time it takes for a particle to traverse a streamline is constant. And the travel time can be written as the rate of change of the area enclosed by streamlines. And so if you rearrange by an area preserving transformation a given stream function, you do not change the area, and therefore you do not change the travel time. And the only work that you have to do then is to actually prove that there is a steady solution which is a rearrangement of the stream function on a new domain. But that's the first result I told you about with Peter, Dan, and myself. So you can arrange for that. And that actually gives you a unique one. Okay, so the point here is that you can deform any of these isochronal ones that you get by such a procedure by adding a little bit of shearing and show they're unstable. So anything that you get here, like the simplest example is the solid body rotation, it's radial. You can always add a little bit of circular flow more in some area, it's still stable, it's still steady, and that thing will directly have this theorem apply. So you can do the same thing here and show that nearby any isochronal thing, there's another steady state which is not isochronal, and thus the isochronal ones are still unstable in C1 alpha. So conjecturally, everything should be unstable in C1 alpha, all the steady states, and it seems like that's probably true. Udovich went even further, and he conjectured that sort of generically, vorticity should grow without bound. Its gradients should grow without bound for Euler. And he says at least this set should be dense enough to show that it's true around any steady state. So this is not just instability, but he's really talking about infinite time growth or infinite time singularity formation. And so with Tarek, we have, again, some result in this direction. We say, if you have a steady state which is stable, so Udovich conjectured for anyone, but let's say you start just with the stable ones, and this steady state has an isolated extremum, maximum or minimum, that occurs either at a single point or on the boundary of your domain. So think of like a radial flow, radially decreasing vortex on a disk. Then for any such steady state, the set of initial data, which is in a ball, for some small epsilon, the set of initial data, which is an epsilon ball of the original one in C1 alpha, or C alpha of vorticity, grows at least like T to the alpha for all time. And so this set is open and dense in that ball in the C1 alpha topology. So what it's saying is that you have your stable steady state, you can find a little ball around it, such that generically in that little ball, all the Euler solutions actually do diverge in C1 alpha like this rate, which is some evidence in direction of Udovich's conjecture. This theorem crucially uses the stability, and in fact, we use Eulerian stability of the steady state to obtain some Lagrangian stability of the flow map that says that transverse to the streamlines of the background, your Lagrangian flow can never move too far. And because of that, you can sustain shearing for all time. So I won't talk about the details particularly, but an example of our theorem would apply to the torus, in fact, where it's sort of steady on the square. So if you have a certain symmetric perturbation, it's steady on the torus. And you have this sustained filamentation and spiral formation. And this grows exactly like to the alpha. Okay. Okay, so now let me turn to a much less clear picture of what happens actually in the limit as time goes to infinity. And let's recall the Euler transport equation is here, and the L infinity norm, the maximum, is just preserved. So because of that, you know that at least the vorticity converges at long times in a weak star sense. So if you can think of that as if you coarse grain the vorticity, then on subsequences of time, you see something persistent always. And you can collect all the things that you see with that procedure, and you call that the weak star closure of the omega limit set. So you're just collecting all the long time persistent motions in one set. That's your omega limit set. And these are the possible end states in this coarse grained sense. Okay. And the goal of, well, one particular goal is to understand what is the structure of this set. What do things look like that are in here? And so there's a couple of just very simple observations you can make. The first is that kinetic energy, being sort of one derivative less than the vorticity, is weak star continuous. So if the vorticity weakly converges to something, then the energy of the things on the sequence is the same as the energy of the thing at the limit. I mean, the energies can converge. So for Euler, it means that any weak limit has the same energy as the initial data, because energy is just preserved. Okay. So that means that energies are robust invariant. You don't change it in this infinite time limit. Whereas there are other things that you can change. So all the other infinitely many conservation laws for Euler, the Casimirs, those could change, because in general, function of vorticity, if it's not linear, is not weakly continuous. And in fact, all you know, for example, is that if f, this function, is convex, then you know the Casimir of the weak limit is less than or equal to the Casimir of the data. Say the entropy of the limit is less than or equal to entropy of the data. That just means that mixing can occur, right? So if you have very fine scale mixing of some blob over time, these filaments will average out if you coarse grain, and it means that the coarse grain solution will have less entropy than the initial data. So this property that the vorticity could mix at infinite time is actually conjectured to be a generic feature. This is a much stronger, in fact, than the conjecture that I mentioned of Udovich before, but it's still plausible that Euler should generically be mixing something of the vorticity at infinite time. Now, that's interesting, but we can also say what more about what should happen. So it's now sort of well understood that there should be an inverse cascade of energy. So not only should the vorticity sort of mix some and energy be preserved, but energy should move to the large scale structures of the largest scales available to it on the domain. And one original argument for this that I know is back to Fjordtoft in the 50s. It's a spectral blocking argument that says that you cannot pile up energy at high frequency because there are two invariants, essentially. Even though one's not an invariant in a strict sense, it still is providing rigidity for energy moving to large frequency. But more than energy not going to large frequency, as I said, you observe it to accumulate in the largest scale. So there's this inverse cascade. And this is largely mysterious from a foundational point of view, how this happens. Here's just some creative license slide. So these flows are maybe to some approximation governed by two-dimensional motions of fluid, obviously with more effects than 2D Euler, but nevertheless, the point is that large-scale features do indeed appear to emerge, either vortices or jets, and these are long-lived. So first observed, the eye of Jupiter was in the 1600s by Galileo, so it's been there for some number of years. Okay, so we want to understand generally how it is that these coherent structures could possibly emerge or why they stay. So let me begin by just making some really naive predictions based on the principle that mixing should occur. The first conjecture would be that mixing should just mix the vorticity everywhere. So you should just replace the vorticity at the long time by its average over the domain, which would mean that this omega limit set consists of just one point, which is the average vorticity. And we can immediately discard this conjecture because, for example, if you take the domain to be the torus, in which case the average has to be 0, then the energy of the average is 0, it's 0 vorticity. But you know that the energy of the initial data is not 0. And so given that the energy is continuous, weakly continuous, it cannot be that this emerges as a long time limit of an Euler solution. So complete mixing is ruled out. The next thing you might say is, okay, fine. How about we mix the vorticity as much as possible as defined by minimizing the entropy, subject to having fixed energy. So we cannot just lose energy. And this becomes a variational calculus problem with Lagrange multipliers. And you find that minimizing the entropy tells you that the minimizer satisfies just this eigenfunction equation for the Laplacian with the smallest positive eigenvalue, lambda 1 sitting there. So the prediction of this conjecture would be that at long times you start to look on subsequences like things in the first shell of the Laplacian. And this is nice in the sense that these things are essentially the largest scale objects that can live on your domain. So it is telling you in some sense that you should expect things to go to large scale. But there are issues with this too. For example, why would you minimize the entropy? Why would you define mixing in that way? There's no dynamical precedent for choosing any one of the Casimirs in particular. And moreover, there's no dynamical precedent for saying that Euler should be maximally mixing, but it's reasonable to start somewhere. Actually, for Navier-Stokes, this theory has a name, well, it's selective decay theory. And there's a sense in which perhaps this theory is sort of true for long-time behavior of Navier-Stokes properly interpreted. Okay, so in this general set of ideas, Ansager made an enormous contribution where he proposed that these coherent structures should be understood on a statistical basis. And the model that he considered was a discretization of the 2D continuum Euler equations by means of point vortices. So he studied collection of positively and negatively signed point vortices, say with the same equal and opposite intensities or circulations. And assuming that so this is now a finite dimensional system. The configuration space is finite dimensional because that's the fluid domain. The phase space is also finite dimensional. He assumed then that the dynamics of this finite dimensional system was ergodic. And under that assumption, he appealed to equilibrium thermodynamics to say that the long-time behavior should concentrate around entropy maximizers. And entropy is defined by like a Boltzmann counting argument on the finite dimensional phase space. You actually derive that these maximizers should satisfy that when you coarse grain them, that coarse grained object looks like a solution of this elliptic problem, which you'll recognize as just some particular Euler steady state. So the Laplacian of stream is some function of stream. And the numbers here, beta and mu, are there to enforce the energy and circulation constraints that come from the finite dimension. This prediction only is valid in the limit of large number of point vortices. And it has interesting qualitative feature, which is that in some situations, there are these negative temperature states, which is easily explained from the perspective that if you have a large amount of energy, and over time, if you converge to some coherent structure, you can't be very distributed. Even though entropy wants to distribute you sort of uniformly on your domain, having the constraint of a big energy means that uniform distribution cannot cut it, and you have to group things into sort of concentrated structures, bring vortices together in order to increase the energy to meet the constraint. So that's sort of that's the negative temperature aspect of this picture. Okay, so that was an extremely interesting idea, and there was many follow-up works on it. Here are some of the contributors there. We can sort of boil it down to 3 steps on Sager's picture. First, you make some finite dimensional approximation of the Euler equation. So you replace the infinite dimensional space with some finite dimensional space. Then on that finite dimensional space, you require that your approximation preserve the invariance you cared about, like energy, and also the phase space volume in finite dimensions. So that's a Liouville theorem. The point vortices do that. And if you do that, then you have a chance of this Poincare recurrence there and ergodicity. Okay, so these two things. And then there's this equilibrium thermodynamic idea that you should you should spend time around states which maximize the degrees of freedom. And these are predicting that you look like a stationary state, according to the previous slide. And there are some, so there are some criticisms to this idea. First, that it involves sort of an illegal transposition of limits between long time and large n. So you, in this picture, you sort of taking infinite time limit and then letting n go to infinity, versus for the continuum Euler equation, you really are letting n go to infinity and then time to infinity. And in this exchange, a lot can potentially happen. You can sometimes justify this picture of commuting the limits for systems that are near equilibrium, but for systems that are far from equilibrium, there are potential obstructions. And in fact, for Euler, there are some sort of explicit examples of this. The wandering that I mentioned earlier of Nadarashvili is a result of Schnirelmann saying that there's actually a global Lyapunov functional for Euler. So something is sort of non-decreasing on the flow and strictly increasing on some big sets. And even for the finite dimensional system, there are obstructions to general ergodicity, like the integrable motions for n vortices, although this by itself may not invalidate the Onsager's ideas, just have multiple ergodic components. It could still work. But more severe than these is that the infinite dimensional system is sort of open in two senses. First, it's mixing, or could be mixing, and there are examples of this where the vorticity really weakly converges, but not strongly, so that the limit has lesser entropy, say, than the initial data. That's open in frequency space, so there's like a sink at infinite frequency. And it's also open in configuration, or it's unbounded in configuration space, in the sense that since the vorticity is just area preserving rearrangements, it's relevant to think of how big the space of area preserving rearrangements is. And in fact, it's known by work of Ilyashberg and Ratu, based on conjecture of Schnirelmann, that the diameter of this group of area preserving diffeomorphisms is infinite. So there's sort of infinite complexity that you can mix up a fluid with in two dimensions. Okay, and sort of both of these points could provide major complications to these equilibrium stat-mech ideas as they apply to Euler. Now, Schnirelmann developed a theory in the 90s for a general property of, or a general prescription for maximally mixed vorticities. So he has some definition of what it means to be maximally mixed. And he shows that those things always exist by use of Zorn's lemma, and moreover, that these maximally mixed functions are actually steady solutions of Euler and having the property that there's some functional relationship between vorticity and stream. So that's an interesting statement, because the maximally mixed idea doesn't immediately have anything to do with the Euler equation. It's just saying that if I have vorticity, which is some area preserving rearrangement, and I can sort of mix that by looking at weak limits. And if I fix the energy, then objects which in that set, which cannot be mixed any further without changing their energy, those are the maximally mixed ones. And those happen to be solutions of Euler. So with Michele Dolce, we revisited this idea, which sort of addresses this open in frequency thing I told you before, because it's embracing this mixing. So to be more precise, let's define the orbit of some initial condition having initial energy as this set of area preserving rearrangements of that initial condition together with those having equal energy. Clearly, the Euler solution lies in this set. And moreover, the omega limit set of the Euler solution is contained in the closure of this set in L infinity. So just looking at all, not coming from fluid flow, but just any weak limit in this set, let's just add it to that. That's the closure. This one is contained in just the closure of the area preserving rearrangement itself, intersect equal energy. So just an example of what this means is if I have a disk domain and vorticity assuming +1, -1 value in the disk, then this set is just all the vorticities between -1 and 1 with equal mean. So it shows that you can get mixing there, right? Because you just mix any value, -1, 1, you can get any value in between as long as you preserve the mean. So that's sort of the meaning of what this closure is. You can do your mixings. And what Micheli and I prove is if you take any strictly convex function, f that you like, and any initial data bounded with energy E0, then there always exists a minimizer in this set of mixed vorticities with some equal energy of a Casimir sort of defined by that f. These minimizers are minimal flows. And moreover, you can effectively find a Lagrange multiplier to make this variational problem not over this funny set, which is very complicated, but over an unconstrained space L infinity by finding a suitable convex function. So we prove any minimizer has the property that there's some other convex function that's related to f, where you can minimize this just with Lagrange multiplier on an unconstrained space. And so it's saying that, well, it's giving a method to find these maximally mixed flows by solving this variational problem. And this last point is actually interesting because using some work that Freddie Boucher had done some years ago, it turns out that any maximally mixed flow is actually in correspondence with some prediction from a Miller-Robert theory. So I won't have time to say what Miller-Robert theory is, but you can think of this procedure that Schnirelmann designed is actually just selecting a subclass of things that come from Miller-Robert statistical theory. Okay, what it says is that no initial datum in L infinity is isolated from an Euler equilibrium if you just account for the conservation laws. So the fact that you can always find such a minimal flow means that there's some mixing of it that's perfectly consistent with Euler at the level of just the fact that Euler is a rearrangement that can reach it. Of course, it doesn't say Euler can reach it, but at least you can't rule it out. Okay. Now, on the other hand, there are some settings for which you can rule out some types of behavior at long time using these ideas. So there's also with Micheli. Here we take the domain to be either a 2 torus or a periodic channel, and we want to find initial data which can never become shear flows. So they're not isolated from stationary states in general by the previous argument, but maybe you can isolate them from some particular stationary states. And so in fact, what we prove is that nearby any shear flow, in fact, it's nearby any point, but let's just state it for nearby any shear flow, there exists a smooth vorticity profile, which is close to that shear flow in L1 of vorticity, but with the property that this set of mixings with equal energy and equal momentum to this given point contains no shear flows at all. And what that means is that in particular, if you start with Euler and with this data, then it cannot inviscid damp to shear. And what this data looks like is you just take your background shear, like Kolmogorov flow, and you put some very localized, almost point vortex, approximations of point vortices just in the flow. And the idea is that those point vortices, if they're very small, like say they have width epsilon and their height is like 1/epsilon squared, then the energy of such a point vortex is like log epsilon. And so it's a huge energy perturbation. And if you try to smear it out in the sense that you're in this set. So you mix consistent with being in this set. What you see is that, well, okay, you have to get, we're asking about shear flows. So you ask what types of shear flows lie in here. And then one can show that all the shear flows that live in here must have energy that's essentially order 1. So you cannot redistribute very high energy point vortex into a shear without changing its energy. And so in this way, you can really rule out the long time motion as being a shear. In fact, what you see based on simulations is either that the point vortices sort of stay almost steady with some perhaps structures that are unsteady nearby, if they're sort of co-rotating with the background, or if they're counter-rotating, they get smeared out, but they form these cat's eye type structures that are persistent. So you never actually go to the shear flow. Okay. Now, in the remaining few minutes, let me say a bit more generally about what you see, not nearby this particular data, but just generically, and some conjectures of some researchers in that direction. So first, if you just start 2D Euler periodic box with Gaussian random data, as is well known and observed, you see mergers of vortices. So it's a slightly viscous simulation, but you see that like sign vortices tend to attract each other as Ansager envisioned, and that over time these mergers happen again and again until you reach some state with, say, 2 or some small number of vortices that are long-lived in the end. And these just sort of wander around the domain in some unclear fashion. Now, it's not the only thing you can see. So from some other random data, you see a very similar intermediate picture, but at the end, you could have other structures like not just a dipole, but this actually looks like a dipole of tripoles where they're counter-rotating and themselves moving across the domain. And perhaps a structure like this could also be infinitely long-lived, although it's not so clear. So looking at simulations of this character, you come to this mysterious question, which is Euler's is this reversible system at finite time. Yet, if you apply sort of any arbitrarily fine coarse graining, and you look at the picture at long time, it looks like a very special set of motions actually appear. And so in a broad sense, there's a decrease of entropy for the system, since you start with sort of a generic thing and you always look like a subset, a very small subset of the available phase space in the limit. And so the question is, how do you understand this decrease of entropy for Euler at long time, at least if one's looking at phase portraits of the velocity field? And there are sort of 2 asterisks here. So one is entropy here, I just mean some general sort of measure of the diversity in the set of possible configurations. So not anything specific. And at least if one looks at the velocity fields, if you look at the configuration space, so for the Lagrangian flow itself, potentially what you see is extremely chaotic and disordered, even if the velocity itself looks sort of structured. And so there's a dual picture on configuration space side where maybe the entropy is increasing, whereas in the phase space, it appears decreasing. But this is, yeah. And so I'll end with these 2 conjectures about this. So one is by Schwerak, who says that, this is what I mentioned before, so generic points in the, say, L infinity phase space for Euler have the property that their orbits are not precompact in L2, which is just saying that at long times there should be some mixing, so that if you look at some arbitrarily fine coarse graining of the long time behavior, it has lesser energy than the initial data. And then there's this conjecture by Schnirelmann, which says that for any initial data in L infinity, if you look at the collection of all its weak limits as time goes to infinity, that should correspond to vorticities which generate L2 compact orbits for Euler. So in particular, they could be steady, periodic, quasi-periodic, but he's characterizing them as the statement that if you start with that vorticity that you get in the limit, then if you reran Euler, you would not see any mixing at infinity. And so if you pair these two together, one saying that the thing you go to is something which is highly non-generic, then it's sort of giving this picture that Euler is a dynamical system that flows the whole phase space, say the unit ball in L infinity to itself at finite time. But if you look at just the collection of all the weak limits unioning over all these points, it's some very small set in that original phase space. And this is obviously a major open and unclear issue, but there are a couple points in its favor. The first is that also a theorem due to Schwerak is that for any initial data in L infinity, this omega limit set for that initial data contains at least one L2 compact orbit. So the thing that Schnirelman says should be the entirety of it is at least there's one of them for any data. And both conjectures are true in some moral sense for neighborhoods around special equilibria. This was first demonstrated by Bedrosian and Masmoudi, and subsequently there's work of Ionescu and Haugia, which say that if you take a monotone shear on a periodic channel and you look in a very small neighborhood and a very strong topology of that monotone shear, then everything in that neighborhood either is a steady state, which is a shear, or at long times it weakly converges to a shear. So it's exactly this picture that things will generically mix, and what they mix to is, in that case, steady states that are shear flows. So these two together. Of course, it's not really generic in like a bigger space like L infinity, because these perturbations are very strong topology, but morally, it's the spirit of it. Oh yeah, so that's it. Thank you.
Many thanks, Theo, for this beautiful talk. It's really a nice finish of our workshop. Let me ask the audience if there are any questions or comments. Yes, Anna.
Hi, Theo. Very nice talk. So I have a question about your first part where you had a bounded domain. So you assume that the boundary is smooth.
Yeah.
Do you have any conjectures if you allow things like a corner or maybe even a cusp or?
Is this in concern? This is concerning which part? The
well, the behavior, right, of the stability and
like this stuff.
Yeah.
If you I know that there are some works, I think, by Sasha Kiselev and on sort of instantaneous or some singularity formation and some strong topology for 2D Euler with corners in the domain or cusps. I have to recall those results. I haven't really thought about that case. I should, but maybe let me not say anything now wrong about it.
Okay. All right.
Good question. Yeah.
Thank you, Anna. Other questions or comments by the audience? Is there anybody on the online? Nobody is online. Thank you again, Theo, for the nice lecture and for a beautiful finish of this workshop. We will wait for a few minutes. I think Anna went to. Oh, Rich, you have a question. Sorry, I didn't see your hand. You're too tall.